Hello, everybody. Welcome back to Mathematical Statistics. We are talking about UMP tests. That's uniformly most powerful hypothesis tests. And we first started with a best test, which is also known as a most powerful test. And a best test is for a simple versus simple hypothesis. And we had a lemma called the Neyman-Pearson lemma, which gave us a recipe for finding the best test or the most powerful test when we have something that's simple versus simple. Then we moved to simple versus composite, and we wanted to talk about not the most powerful test, but the uniformly most powerful test. Uniformly in math meaning for all. And this test for a simple null hypothesis with a composite alternative is the best or most powerful test for every simple versus simple you can choose by choosing individual simple hypotheses out of that alternate hypothesis. And so the approach is usually to do just that, to use the Neyman-Pearson lemma, and to show that your ultimate test does not depend on the particular choice you made. So let's just jump right back in with an example. For my first example, suppose that we have x1 through xn IID from a continuous distribution with this kind of strange looking PDF. So I'm going to have a parameter theta, and this is going to be 1 minus theta squared times x minus 1/2. And this whole PDF has support 0 to 1. So I'm going to multiply by an indicator 0 to 1 for x. And the parameter space, just so this makes sense and doesn't turn into something that's negative or integrating, well, mostly so it doesn't turn into something negative. The parameter space, the capital theta, is going to be everywhere from -1 to 1. So those are the allowable values for the parameter theta. Let's find if it exists A, and I want to say V. I need to talk a little bit about uniqueness. These are unique, so I could say V. A UMP, uniformly most powerful test of size alpha for testing the null hypothesis that theta equals 0 versus the alternate hypothesis that theta does not equal 0. So simple versus composite. And I want to make this sort of exactly doable so we don't have to approximate a critical value. So for that reason, I'm going to really simplify this problem and say based on a sample of size 1. So really, instead of x1 through xn, I just have x1. Okay, so step 1 in finding a UMP is usually to consider first a simple versus simple scenario. I'm going to keep my null hypothesis. And then for the alternative, I am going to say theta is some specific theta 1, or this is any number that's not 0. So it's fixed. And again, theta 1 is not 0. So now I have a simple versus simple, and we can apply the Neyman-Pearson lemma. Usually the first thing I do is write down the joint PDF, but because we only have a sample of size 1, I've got basically the joint PDF up here. So this is the PDF. It is the joint PDF, if you will, because again, remember that n, our sample size, is 1. So we're only working with a capital X1, not x1 through xn. To use the Neyman-Pearson lemma, we want to make the likelihood ratio. We've been calling this lambda. Usually I have a whole vector of x's here, but there's only one x, so I'm just going to write it like that. And then we have the null hypothesis parameter, which is 0, and the alternate hypothesis parameter, which is theta 1. This is going to be f of x and 0 over f of x and theta 1. Now in this ratio, we have this indicator in both the top and bottom, so that's going to cancel. And for the numerator, if I plug in 0 here, I'm just left with 1. So this is going to be 1 divided by 1 minus theta 1 squared times x minus 1/2. Now we want to set this less than or equal to k. And the form of the test is going to be to reject if you go and observe your x1 and you put the capital X1 in here, and this thing is less than or equal to k, and that's valid, but usually we rewrite these things in terms of, smaller base units and statistics. Also, I don't know how to find k in this form. So let's start rewriting this. I'm going to flip both sides over. So when I take the reciprocal, that will flip the inequality. And on the right side, I'll have 1 over k, which I'm just going to call k1. It's a new constant. I'm going to subtract this to the other side. Now, you don't need to do this in so many individual steps, but that'll give me a new constant, k2. And now I want to divide by this. So theta 1 was chosen to be some number that was not 0. So we're not dividing by 0. That's a good thing. But this thing is always negative no matter what theta 1 we choose, theta 1 above 0 or theta 1 below 0. So when we divide, we're going to flip the inequality again and get some other constant k3. And then finally, I'm going to move the 1/2 over to get some constant k4. So that is just the algebra. The form of the best or most powerful test of size alpha is to reject the null hypothesis in favor of the alternative. It's important to write that when your two hypotheses do not make up the entire parameter space. If our x1, our random variable, our random sample, is less than or equal to some k4 to be determined. So that is the form of the test. And to finish this out and actually find the test, we need to find k4. Once again, I want to remind you on the upcoming exam, watch out for form of the test. It might be all you have to do. You might be able to stop at this point. Okay, so this is still step 1, but I want to find k4. So alpha is going to be the probability of making a type 1 error. This is the probability we reject the null hypothesis when the parameter is theta naught. So this is saying the null hypothesis is true. If we had a composite null hypothesis, then we'd need a maximum or supremum over a bunch of probabilities where we'd be running over all different values from the null hypothesis here, but we only have one. And rejection for us is that our single sample x1 should be less than or equal to some k4 that we're trying to determine. I wrote the theta naught. Theta naught is 0, so I'll just put that on the side. I should have put 0 inside both of those statements. So we need to compute a probability using the given PDF when theta is 0. So take a look right here at the PDF. If theta is 0, this entire part disappears. And what we're left with is a PDF that is 1, it's a constant on the interval 0 to 1, which is the uniform 0, 1 PDF. So when theta naught is 0, that means that x1 is uniform on 0 to 1. And because there's only one, our sample only has size 1, we can find this pretty easily. If you imagine a uniform PDF on 0 to 1, it's going to be of height 1. And so we want to find a number, k4, that will be less than or equal to with probability alpha. Now, alpha is the area of that rectangle, and the height is 1. And this means we need k4 to be alpha. So for the end of step 1, okay, so the best or most powerful test of size alpha for this problem is to reject the null hypothesis in favor of the alternative if x1 is less than or equal to alpha. That's the test. Pretty simple looking test, but it was a pretty simple looking problem. So this is the best or most powerful test for the null hypothesis that theta equals 0 versus the alternative that theta is some theta 1, where theta 1 is a fixed number that is not 0. But those are not the original hypotheses that we care about. We had that our alternate hypothesis was all the theta not equal to 0. So if you look at this, you'll note that there's no theta 1 in there. And theta 1 may actually have affected, our choice of theta 1 may have affected this if, say, when we divided by theta 1, if it was positive or negative, something would not flip or flip. But you'll notice that when that actually happened in this problem, we divided by a negative theta 1 squared. So if theta 1 itself is positive or negative, you square it, that's positive. You take the negative, that's negative. We will always get the flip. So our final test does not, in this circle, appear to depend on theta 1. And the direction did not depend on which theta 1 we chose out of all of the theta 1s in the alternate hypothesis. So this test does not depend on the theta 1 chosen. Again, that's two things there. There's no theta 1 in here, and the choice of theta 1 did not affect whether or not we're going to flip that inequality. Thus, it is the UMP test of size alpha for the null hypothesis that theta equals 0 versus the alternative that theta does not equal 0. I bring up this example for a reason. A lot of people will claim that you will not have existence of a UMP test whenever you have a so-called two-sided alternative like this. But for this particular problem, we did because things, were constructed just right. So if you have a not equals or a two-sided alternative hypothesis, very often a UMP test does not exist because you'll get maybe a test like this, and maybe the test will look like this for the other theta 1s you could have chosen, and there isn't one that works for all theta 1. But we had one here, so we're done with a UMP test for a two-sided alternate hypothesis. Let's do one more UMP. I'm going to take a random sample, x1 through xn, IID from a distribution with PDF f of x and theta is going to be theta x e to the minus theta x squared over 2 on the interval from 0 to infinity. And the parameter space here is going to be all theta is greater than 0. Otherwise, you're going to have trouble. Let's find if it exists. I keep writing this because I want to give you a problem on a homework or an exam where it doesn't exist. And if I just start writing that all of a sudden, that's going to be a key that it doesn't exist. So I'm writing it every time. If it exists for the null hypothesis that theta equals 1 versus the alternate hypothesis that theta is greater than 1. Okay, I'm going to use Neyman and Pearson. So step 1 is to consider first a simple versus simple hypothesis. So I'm going to leave my null hypothesis because it's already simple. And then I'm going to choose my alternate hypothesis to be theta equals some fixed theta 1, where theta 1 is a fixed number that is known to us and is greater than 1. The joint PDF, I am going to go ahead and write this out as if I had plugged in my xi and multiplied. I'm going to get theta to the n, a product as I goes from 1 to n of the xi, e to the negative theta squared over 2 sum of the xi, and a product of indicators. since we've gotten into general hypothesis testing, I really haven't done anything, I think, with the parameter and the indicator. I will do some examples, if not today, on Wednesday. Okay, so now I'm going to form the likelihood ratio. This is a lambda of the vector of x's, the null hypothesis parameter, and the alternate hypothesis parameter. This is the joint PDF with the null hypothesis parameter plugged in over the joint PDF with the alternate. And I am going to not write the whole thing out. I'm going to try to simplify as I go. So both numerator and denominator will have this. It will cancel. Both numerator and denominator will have this, and it will cancel. And we will be left with 1 over theta 1 all to the n. In other words, 1 to the n over theta 1 to the n. E to the negative. I'll write this. Sorry, I got to plug in the 1. So E, or let me do this over here. So my top exponent, come on, chalk, is minus 1/2 sum of the x's, and then I want to add theta 1 squared over 2 sum of the x's, and those x's were squared. They were squared. So right here, they should be squared. Sorry about that. Those are squared, squared, and squared. Anyway, this is the exponent for the e, so I'm going to say minus 1/2 1 minus theta 1 squared sum of the xi squared. Did I get that right? Looks pretty good. So there is the likelihood ratio for the Neyman-Pearson test, and we're going to set this less than or equal to some constant k to be determined. I'm going to try to isolate the x stuff. So I'm going to do a few things at once now. I'm going to divide this to the other side. Theta 1 is greater than 1, so I'm not dividing by a negative or anything like that. I'm also going to take, after that, the natural log of both sides. And neither of those operations are going to flip the inequality. And that's going to bring me to negative 1/2, 1 minus theta 1 squared, sum of the xi squareds are less than or equal to, I want to say k1, but maybe it's your k2 or k3 if you did those steps individually. It's just another constant. And then I want to divide by this thing. So our theta 1 was greater than 1. And when you square it, that's also greater than 1. That makes this thing negative, which makes this whole thing positive. So when we divide, we are also not going to flip anything at this stage. So the form of the best or most powerful test of size alpha, or level of significance, for the null hypothesis that theta equals 1 versus the alternate that theta equals some theta 1, where theta 1 is known to us and greater than 1, is to reject null hypothesis in favor of the alternative if the sum as I goes from 1 to n of the capital Xi, here we're making a statement involving randomness, and someone's going to go take the sample and eventually have numbers here, is less than or equal to k2. The form of the test, that's enough, but I want to find k2. So I want to find the actual test. That was the, that was the instructions given at the original, at the top of the problem. So we're still in step 1, but I want to find k2. Let me go grab this PDF. And we find probabilities for this statistic. Can we find them for just one of those? So just like an x1 squared. And what I'm about to do, I'm just going to call it x. You can call it x1. But I want to look at the distribution of y defined to be x squared, or y1 defined to be x1 squared. Again, just doing the algebra and stuff, so I'm not carrying the subscripts through. This is a G problem, a G inverse problem. And so we want to invert this. Now, x squared is not invertible in general, but it is invertible if all the x's are positive. So this is going to be the square root of y, the positive square root of y. Now, the PDF for y, and you can go ahead and put your semicolon theta, but I'm sort of going back to when we were talking about the G inverse stuff. And at that time, we didn't write that. Please go ahead and write it if you're okay with it. But I want to look at the PDF for x with G inverse y plugged in times the absolute value of the derivative with respect to y of G inverse y. So I'm going to take the top line and I'm going to put the square root of y in for every x. We'll get theta square root of y e to the minus theta y over 2, because that was the square root of y squared, an indicator saying that the square root of y is between 0 and infinity, and then the absolute value of the derivative of this being y to the 1/2. So we'll get 1/2 y to the negative 1/2, or 1 over the square root of y. And that is nice and positive already. So I can drop the absolute value. We are going to get this ugly square root of y to go away. That's pretty nice. And I'm left with 1/2 theta e to the minus theta over 2y. And this indicator, if you just write down that the square root of y is between 0 and infinity and square it all the way across, you'll get that this holds for y's between 0 and infinity. So let's just rewrite this. So it's an indicator in terms of y alone. This is an exponential PDF. So if x1 has the given distribution, which is a Weibull distribution, by the way, x1 squared is exponential with rate theta over 2. We can handle exponentials. We've been doing that since the very beginning. Remember, I'm trying to solve this sort of problem, and I want to compute I want to compute a probability that it's equal to alpha under the assumption that the null hypothesis is true. The null hypothesis here was that theta was 1. So let's do it. Alpha is the probability that the sum as I goes from 1 to n of the xi squared is less than or equal to whatever I was calling that constant, k2, when the parameter is 1. And so not only do we have an exponential, but we have an exponential specifically with rate 1/2. So this is the sum of n IID exponentials, each with rate 1/2. And we know that when you sum exponentials, you get a gamma distribution. The first parameter is the number of things you added, and the second is matching the exponential rate parameter, assuming you parameterize your gamma distribution the same way I do. This is clearly going to chi-squared territory. I can't find critical values for the gamma distribution in closed form. If I actually have data and numbers and an n, I can do that numerically. But to get this to a nice form, let's write it in terms of a chi-squared critical value. So the chi-squared n is gamma n over 2. Oh, we are there. We are there already. So we have a gamma 2n over 2 and 1/2. Usually at this point, we are trying to get that second parameter to be 1/2 by multiplying by stuff. What we have seen is that when the parameter is 1, this is chi-squared 2n without having to adjust to anything. I want to look at the chi-squared distribution, just draw a generic PDF on 0 to infinity, and I want to be below a number k2 with probability alpha. Our critical values, the way we've been writing them in this class, they use notation that specifies the area above. So our k2 is going to be chi-squared sub 1 minus alpha, comma 2n. So for the end of step 1, the best or most powerful test of size alpha of the null hypothesis that theta equals 1 versus the alternate hypothesis that theta equals theta 1, where theta 1 is a fixed number greater than 1, is to reject the null hypothesis in favor of the alternative if the sum, as I goes from 1 to n, of the xi squared is less than or equal to this chi-squared critical value that cuts off area 1 minus alpha in the upper tail and has 2n degrees of freedom. Okay, so this is another fun problem that brings together all of our skills for the entire semester. We were not originally looking at these hypotheses, though, but you'll note two things. One is that this does not, at first glance, it does not appear to depend on theta 1 in that there's no theta 1 in the thing I just boxed off. But it could depend on the particular theta 1 we chose from the original alternate hypothesis. What is the word? This for the alternate hypothesis. It was theta greater than 1. While I don't see a theta 1 in this box, we did use the fact that theta was greater than 1 right here. It made that coefficient positive so that when we divided to isolate this, we still had a less than or equal to. So this thing in the box at the very end does not have a theta 1 in it, and this direction only depends on theta 1 being greater than 1, not the particular choice. So I guess I should call this step 2. The test is uniformly most powerful for the null hypothesis that theta equals 1 versus the alternative that theta is greater than 1. Our second beautiful UMP test for today. So I want to talk briefly about a composite null hypothesis and the UMP test. We had a best test, which was simple versus simple, and then we kicked it up to UMP, which was simple versus composite. And now suppose that we have a composite null hypothesis, and the alternate could be simple or composite, but it would be really strange to assume, say, that lambda was less than or equal to 3 and be out to prove that it's actually equal to 8. In theory, you could do that test, but what I care about here is that there's a composite null hypothesis. So something like x1 through xn, IID, exponential with rate lambda is fine. Then I have lambdas of lambdas, which is also fine. Or you can denote your likelihood ratio with something different. I just think it's easiest right now for me to call this parameter theta. And suppose I wanted to test something like theta is less than or equal to 1 versus theta is greater than 1, and I want to find the UMP test if it exists. If you go back and look at our proof of the Neyman-Pearson lemma, which was last class or the class before, it was for a simple null hypothesis. But you can trace through that proof and see that if the maximum you have to compute, so the maximum over all theta less than or equal to 1 of the probability that we reject the null hypothesis when the parameter is theta, if this maximum occurs on the boundary that breaks these up, the boundary between the null hypothesis and the alternate hypothesis, you can trace through our proof and see that it will still hold. So the Neyman-Pearson lemma still holds. This is not hard to show at all, but in the interest of time, I'm not going to drag out the old proof and just go and change those things. It's really straightforward to change that up if you have the proof in front of you. So if we want to find a UMP test here, we can try Neyman Pearson on like theta equals 1 versus theta is some theta 1, where theta 1 is greater than 1. Like just looking at the boundary here and just looking at any point in the alternate hypothesis so that we can use Neyman Pearson. And if you get a test that does not depend on the particular choice of theta 1, then your best or most powerful test is then UMP for theta equals 1 versus the alternative theta is greater than 1. And if the cutoff that you determined when doing this test had a maximization step, and if that maximization occurred by plugging in theta equals 1, which is right on the boundary between the null hypothesis and the alternate, then Neyman Pearson still holds. So this is UMP, and then this, sorry, that's not a test, but whatever test you get for this, so this will give you a test, it'll give you a statistic and a direction. You can show its UMP for this by the same thing we did in the first two examples today. And then you can extend it and it will be UMP for this if alpha is the probability that the maximum over theta less than or equal to 1 of the probability you reject the null hypothesis when the parameter is theta. If this max occurs at theta equals 1 on the boundary between the null hypothesis and the alternate. So that happened maybe every time for us so far in this class. I'm not 100% sure, but it's happened the vast majority of the time. So you're going to be able to use Neyman Pearson to find a UMP test for lots of composite versus composite hypotheses. Not for the crazy ones that we haven't done yet, but I've talked about, like the null hypothesis is all theta for which the sine of theta is greater than 1/2, like doing really weird regions. But for the equals, not equals, less than, greater than, less than or equal to these things, you can use the Neyman Pearson to find a best or most powerful test, extend it to a UMP test, and then make sure that's still going to hold when your null hypothesis is composite. Now, if the maximum does not occur on the boundary, it doesn't mean that a UMP test doesn't exist. It just means that you can't use the Neyman Pearson lemma. And in fact, I don't have a recipe for you. Here's where you're going to have to get creative in your research to derive your own test, hopefully using some of your skills from this course. And it's going to be really problem specific. But remember, when you want a UMP test of size alpha, even if you're not using Neyman Pearson, just remember what it means. It means you do want a test of size alpha, and you want your test to have the highest power over all tests, over all values in the alternate hypothesis. Most powerful. Okay, so what I'm about to talk about now, you're not going to be tested on, but I do want to do one discrete hypothesis test example, just to talk about some pitfalls, some language, things you might see. Yeah, so let's do it. Let's pick one. How about I want to look at some things numerically here, so I'm going to make this a sample of size 10. I'm going to fix my n, and I'm going to suppose that these are IID Poisson with parameter theta, say. And let's just look simple versus simple because this is going to be complicated enough. Let's find the best or most powerful test of size alpha for the null hypothesis. Again, I want this to be a really concrete problem, so I'm going to take theta equals 1 just because I've been doing that all day, but things simplify nicely, versus something like theta equals 3. We do need a positive rate parameter for the Poisson. Okay, so we're going to use the Neyman Pearson lemma, and we're going to need the joint PDF. So I am going to rush a little bit ahead here. The original PDF is going to be e to the negative theta, theta to the x over x factorial. When you plug in xi and multiply them, you're going to get e to the negative 10 theta, theta to the sum of the x's over the product as I goes from 1 to n of xi factorial. And the x's that can go in here are non-negative integers, 0, 1, 2 on up. I'm going to try to apply the Neyman-Pearson lemma here. So I'm going to look at the likelihood ratio. I'm going to look at it with a 1 and a 3. In other words, the joint PDF with theta equals 1 in the numerator and the joint PDF with theta equals 3 in the denominator. Now, this does not involve theta. So when we form that ratio, the thing I just circled is going to cancel away completely. And we're going to end up with e to the negative 10, 1 minus 3, and then 1/3 to the sum of the x's. So I'm going to set this less than or equal to k for some constant and try to get down to the x's. This is, of course, -2, which makes this positive 20. So if I divide, I will get 1/3 sum of the x's less than or equal to some k1. And to get at that sum of the x's, I'm going to take the log on both sides. So I'll bring down the sum of the x's in front, the log of 1/3 less than or equal to the log of k1. Now the log of numbers between 0 and 1, is negative, right? Here's log. So this is a negative number. And when we divide and try to isolate the x's, we will flip. This could have been called k2 already. And now when I take the negative, I'll call that k3. So that's going to be the form of the test. We're going to want to reject the null hypothesis in favor of the alternative if the sum as I goes from 1 to n of capital Xi is greater than or equal to some constant k3, where k3 is to be determined. And here we're going to have some trouble because of a discrete distribution. And this is the same sort of trouble you would have no matter how you did this hypothesis test. Maybe not using Neyman-Pearson. Maybe it wasn't even supposed to be a best test. If you did what we did back in the earlier part of the course when we first saw hypothesis testing, you might say, well, I'm going to base my test on the sample mean x bar, and I should reject this in favor of this if x bar is large. And that's essentially what we're getting even after Neyman-Pearson. I could put a 1 over n on both sides of this. So we have a rejection rule, no matter how you got it, whether you're trying to find a UMP test or not. We need to find K3, and because of the discrete distribution, we are going to run into some trouble. So I want to talk a little bit about options. I'm going to let S be the sum as I goes from 1 to n of the xi, and the sum of IID Poissons is again Poisson with parameter n times the original parameter. So alpha, did I give an alpha? I didn't give an actual alpha, but since everything else has actual numbers, let's use a 0.05. So I want to get 0.05 as the probability that, should I write this? I'm going to change this notation here. And I'm going to say that S has a Poisson distribution with parameters n times 1. N was 10. So parameter 10 when the null hypothesis is true. So all I did was take my theta n, but theta was 1 from the null hypothesis and n was 10 because that was our sample size. Okay, so now I'm just going to say S greater than or equal to K3. And as long as I have it in the description of the distribution of S, I don't need to write semicolon anything anymore. I don't have a nice expression for this cumulative probability. The The first thing I'm going to do is turn both sides around. So I'm going to look for 0.95 as the probability that S is strictly less than K3. And that strictness is important because we're working with a discrete distribution. And again, S has the Poisson 10 distribution. So now I'm going to try to find K3 by some trial and error. The probability that S is less than 0, well, that's not happening. That's 0. The probability that S is less than 1 is the probability that S equals 0. That's the only way a Poisson can be less than 1. And this is going to be e to the minus 10, 10 to the 0 over 0 factorial, or e to the minus 10, which, just for your information, is approximately 0.000045 and nowhere close to 0.95. I'm going to write one more out. The probability that S is less than, say, 2. This is going to be the probability that S equals 0 plus the probability that S equals 1. When you add these together, they're both going to have an e to the negative 10, and then the S equals 0 case, we're going to get a 1, and the S equals 1 case, I'm going to get 10 over 1 factorial. Yeah, so this is 11 e to the minus 10. And if you calculate that, that's still not 0.95. It's below 0.95. So before I continue, I do want to say something like, what is the probability that S is less than? Like, why am I looking at integers here? Because the K3 does not have to be an integer. These are the only points I have to look at, because if I say the probability that S is less than or equal to 1.7238, because it's non-negative integer valued, this is the same thing as the probability that S is less than 2, which is going to be 11 e to the minus 10. So I'm just looking at these integer values, but all values are important. Either way, this thing is approximately 0.0004 or something. So we've moved up, but we're still not at 0.95. So then I did this on a computer. I calculated these things recursively on a computer. I kept adding probabilities, and here is what I got. I got the probability that S is less than 15. This was approximately, I did everything exact, but I'm writing an approximate answer. Approximately 0.9165415. So I didn't quite make it to 0.95. And now I'm going to look at the probability that S is less than 16. And this is where I jump over the 0.95, and I got 0.9512596. So in other words, I'm solving S less than some, whatever it was, K3. And when K3 was 15, I got something under where I need to be. And when K3 was 16, I got something over where I need to be. Let me, just so we can really get a handle on what we're doing, turn things around here. We wanted our alpha, which was 0.05, to be the probability we reject. So in the first test here, I would reject when S is greater than or equal to 15. And that probability would be 1 minus this, which is approximately 0.08 something. The other test is I'm going to reject when S is greater than or equal to 16. So if I take 1 minus this is going to be approximately 0.0487. So if you're trying to control your type 1 error, and you might not be, you might want to control your probability of making a type 2 error, and you want that to be less than or equal to, or you want that to be equal to 0.05, usually you would go with the lower one, which has smaller probability of having a type 1 error, which is conservative if you care about type 1 errors. So one option here is to report your test like this, is to say, I'm going to reject the null hypothesis that theta equals 1 in favor of the alternative that theta equals 3 if the sum as I goes from 1 to 10 is of the xi is greater than or equal to 16. Now, this test has size 0.0487. To me, and to a lot of people out there and a lot of books, we would also say this has level 0.0487. But some people do distinguish between size and level in the case of these discrete tests where things like this happen. You could say this has size 0.0487 or level of significance 0.0487. But some people will say this test has size 0.0487, but level 0.05. And level is sometimes an upper bound on size when you can't reach the size exactly, which is something that happens for discrete distributions. I'm not going to test you on that or even use that language. So this end of option 1 is that we have an approximate test of size alpha. It's really of size 0.0487. But again, size and level are sometimes defined a little bit differently in the discrete case, or in all cases, but you don't see it in the continuous case. Option 2 is to make the test exact using something random, like look at some of the x's and say, oh, it's greater than or equal to 16, and also I flipped some coin and got heads. Seems a little weird because it doesn't involve the data, but it'll get you to the actual size you want. So for this example, it's the same example, but it's an example of something random. You might say, I'm going to reject the null hypothesis in favor of the alternative if the sum as I goes from 1 to 10 of the xi is greater than or equal to 16, or I'm going to reject if the sum as I goes from 1 to 10 of the xi is equal to 15 and my strange coin comes up heads. So I'm going to use a biased coin where the probability of getting heads is going to be, well, what it needs to be. So the probability you reject when the null hypothesis is true, so theta is 1 and we're working with a Poisson 10, our alpha is going to be the probability that the sum as I goes from 1 to 10 of the xi is greater than or equal to 16, or we get to add the disjoint event probability, so I still need to figure this out, of the probability that the sum as I goes from 1 to n, or 10, of the xi is equal to 15, and then multiply by an independent coin flip for a really strange coin. So we know this number, 0.0487, and this number was, so this is approximately 0.0347187. So I'm going to put that in here. When I actually do these computations, I would worry about significant digits and stuff, and I would keep everything exact until I can't anymore. But times the probability of getting heads. And this is 0.05. So if you solve this for the probability of getting heads, this must be approximately 0.0374. Looks a lot like this number, but not. So I need a strange coin like this. And then my hypothesis test is going to be, you reject outright if your sum is greater than or equal to 16. But if you're seeing 15, or you're kind of borderline, then flip a coin, not a fair coin, but a coin. And in practice, you're going to be grabbing a number from a random number generator to serve as this coin flip. So now we have exactly, except for maybe my rounding error, a size and level alpha 0.05 test. What I did here had nothing to do with, well, it did have something to do with the Neyman-Pearson lemma. That's how we got the statistic. But then we did some strange things. But it turns out that this and I'm not going to prove it, but this procedure here with this randomization, this test is actually UMP, uniformly most powerful. There is a different version, a more general version of name and Pearson. So I'm not testing you on this, but we had some setup, right? And we formed a likelihood ratio. And the name and Pearson that we've looked at says to reject if this thing is less than or equal to K. But if we follow the rule reject if this thing is strictly less than K, and if this thing is equal to K, reject with some probability. It's usually called gamma, although I use gammas for, let's call it little p. P. Otherwise, fail to reject. So now to finish this test, you need to find the K and the P. And this is a different version of name and Pearson. That will give you the UMP, uniformly most powerful test. And in fact, if you want this to be your only version, that's okay, because what we've been doing so far has been continuous. So no matter what this P is, this is not going to happen with any positive probability. And in the continuous case, this is the same thing as the probability that this is less than K is the same thing as the probability that this is less than or equal to K. So this could be your generic name and Pearson. And in the continuous case, these sort of collapse into one, and there's no extra probability to have to work out. I hope this summer to be able to write that up for you. And it's going to end up in the second edition of my MathStat text, but that's a ways away. My Markov text is the next one to come out. So yeah, I'm just going to leave that there in the interest of time, which we have very little of. For the purpose of forward momentum, let's talk about our final test in this course. And we're back to material that can be on your final. So all that Poisson, all that discrete stuff, level versus size, the additional name and Pearson, I'm not going to test you on any of that. But our final test is called the Generalized Likelihood Ratio Test. We already had something that could be called a likelihood ratio test because it was based on a ratio of PDFs, which is equivalent to a ratio of likelihood functions. The UMP tests, they do not always exist, and they can be really, really hard to find if you don't have not literal simple hypotheses, but simple in the English language sense, less than, greater than, less than or equal to. You know, if you start to have those really wacky hypotheses that I've been teasing for some time now. So let's go back to our general setting where theta is, so we've got a parameter space and I'm calling it capital theta. And we have a subset of the parameter space that I'm calling capital theta naught. And the null hypothesis is going to be that theta is in theta naught versus the alternative that theta is in the rest of the space. So the capital theta, and then we'll take away theta naught, or we'll intersect it with theta naught complement. The generalized likelihood ratio test gives us a statistic and a direction to start with, just like name and Pearson. We want to look at the so-called generalized likelihood ratio. I'm going to call it lambda, but there's no lambda naught and lambda 1 here. I have pretty general looking hypotheses, so I'm going to call it lambda of just the x's. And I am going to take either the joint PDF or the likelihood. And in the numerator, let me write these likelihoods down. I am going to plug in the value that maximizes the likelihood when restricted to the null hypothesis being true. This will become clear when we do examples, but I'm going to write the maximum over all theta in this capital theta naught, that is the null hypothesis region. In the bottom, if you wanted to put the maximum over this, you wouldn't be wrong. There's many ways to build your own test, but I'm going to do something a little bit different. I am going to maximize over all theta in the entire parameter space. If I put this there instead, it would still make sense in that it is a ratio that will be smaller when the alternate hypothesis is true. So I'm looking at the likelihood, which is the likelihood, and I'm plugging in the maximum value of each. So I'm looking at the high point for each likelihood. And if the high point of the likelihood in the alternate hypothesis region is higher than it is in the null hypothesis region, that is evidence to reject the null hypothesis. So that's what you would get if you maximized the denominator over this. This is a different test. And the reason we do it is because we have nice properties here. So, the big problem usually comes from finding the C, finding the K, finding the K4. And that can get intractable really fast. So I talked about how the UMP test is like the UMVU, hypothesis testing versus estimation. Awesome, great, might not exist, probably really hard to find for a real life problem. In estimation, we move to the MLE, the maximum likelihood estimators, which I call the workhorse estimators of statistics. Those are the ones you're really going to be using a lot of, especially if you're doing real data stuff. And the MLE version in hypothesis testing is this. This is the test that's going to be useful more often, work more often. No, it's not uniformly most powerful, but we're going to see it has really good properties and that we're going to be able to compute probabilities more often than not, at least if we have a large sample. In other words, I am going to be setting this less than or equal to some K, and I have some large sample, a cool large sample theorem that will get you the distribution of almost this. It's going to be, we're going to multiply and divide by some things. None of this makes sense until we see the example. So we're going to do that next time. But the first thing I'm going to do, I realize none of this made sense. I tried to fit it in at the end. First thing I'm going to do is several examples of this versus this. So one more thing I just want to get in here. You can write this as, in the denominator, L of theta hat, where theta hat is the MLE. That's what maximizes the likelihood. And in the top, we're going to write L of theta naught hat. And we're going to define that. So theta hat is going to be the maximum likelihood estimator, and theta naught hat is the so-called restricted MLE. This means that we're going to look at a function of theta, the likelihood, and we're not going to just try to maximize it. We're going to look only at the region where the null hypothesis is true and maximize it in there. I kind of regret starting this because I made it sound confusing by not actually getting to anything. So I really hope you come back next time on mathematical statistics.